Okay guys, so today's lesson is on solving systems of equations by substitution. Our essential questions for today's lessons is how do you solve a system using substitution and how does it compare to graphing? So in total we need to know that there are really three methods for solving systems. We learned about graphing last week. Right now we're about to learn about substitution, and in the next few days we'll learn about elimination. Our hope is that by the end of this unit, you know how to solve using any of the three methods, but not only how to solve, but when is the best method to use each of the methods. Really, it's going to depend on the way that the equations are already set up, and as you practice with different methods, you might find that you just like one more than the other, or find that you're more successful, and you'll probably lean on that one, but hopefully you become fluid with any of the three. So how have we seen substitution in the past? In the past, we've seen substitution looks more similar to one of these types of examples. Sometimes they would give us an expression or an equation, and then they would give us values for any of those variables. Sometimes they would give us values for several different variables. So in this particular example, 2x minus 4 equals y, they're asking us to solve the equation for y if x is equal to 7. So we would basically take this number and substitute it where the x is into the equation. So we would have 2 times 7 minus 4 equals y. 2 times 7 is 14. Then we have minus 4 equals y. And so 14 minus 4 is 10. So we find out that y is 10. Well, even though you didn't know it at the time, that is actually a system of equations. We now know that x equals 7 is one of those special kind of lines, those vertical lines, that go through the x-axis when x is equal to 7. So we would have that vertical line. And then truly, when we're looking at this, this is another equation, y equals 2x minus 4, where our y-intercept would be negative 4, so I'm kind of making it up here. And our slope would be 2, so I'd go up 2 over 1, up 2 over 1, up 2 over 1, and I'd keep doing this for a while until they intersected. And they're actually going to intersect at the point 7, 10. I know that because when x is 7, y is 10. That's actually the point of intersection for this system. So that's from graphing. We learned that last week. You had to be able to graph each of the lines and find out if and where they intersect. And now we're going to focus more on this approach. So substitution method is very similar to this example. The big idea here is that we must have a variable that is equal to a number or an expression. This time we had x is just equal to a number. Sometimes it might be more than just a number. So before we get too far into the lesson, let's go ahead and fill out our main ideas. So for substitution method, it is essentially just a method of solving systems of equations by substituting equations within one another. So the steps to solving, so this is kind of a 1, 2, 3 every time what you're really doing. So step 1 is going to be to isolate or solve one of the equations for either x or y. Up until this point, we've been really only familiar with isolating y, like getting y by itself. But in this method, you can technically get x by itself as well. I just have to have one of them, either x equals something or y equals something. Once I have that, I'm going to substitute the expression, whatever it is, into the opposite equation and solve for the variable. Step 3 is going to be to substitute the answer that I get for the first variable back into the opposite equation and solve for the opposite variable. So sometimes we'll understand what x is first and we'll plug that value back in to find y. Sometimes we'll end up solving for y first and plug that back in to find x. So the whole goal here is still the same thing as solving by graphing. I want to know if these two lines are going to intersect, and if they do intersect, I want to know their point of intersection. That's why anytime I find out what x is, I must also know what y is, because I need the ordered pair x, y to give the solution. So we've got number 1, and it should be the same as what is on your worksheet. And if you'll see, our two equations are y equals 4x minus 1 and y equals 2x minus 5. Well, the whole idea here is very similar to that first example. If they had just said y equals 4, I could just pop a 4 in right there where y is. Well, they're saying y equals 4x minus 1. Well, if that's truly what y is equal to, I can replace y in the opposite equation with that expression. So when I do that, I have a whole new equation that I can actually solve. And the reason why I can solve it now is because x is the only variable involved. If I have more than one variable in the same equation, I can't actually get a number answer for either one of them. But now that I only have an x in the equation, I can actually solve this like we used to do and find out what x is equal to. So I'm going to work 4x minus 1 equals 2x minus 5. We think way back when we were starting to solve equations, I've got variables on both sides, and I want to try and get them together. Usually we move the smaller coefficient. Since 2x is positive, I would need to minus it from both sides. Cancels out over here. 4x minus 2x leaves us with 2x. Bring down the minus 1 equals negative 5. I need to move over the minus 1 by adding it. I've got 2x equals negative 4. Divide by the 2, and x is equal to negative 2. So I now have an x amount, but I need an actual ordered pair. I need an xy. So far all I know is the point where they intersect is negative 2 something. So to find out what that y coordinate is, where they intersect, I'm going to now take this x value and I'm going to plug it back in to one of the original equations. So if I've got this negative 2 for x, I could plug it back into the first one. I would have y equals 4 times negative 2 minus 1. So y equals negative 8 minus 1. So y equals negative 9. If I plug it into the other one, I have y equals 2 times negative 2 minus 5. So y equals negative 4 minus 5. So y equals negative 9. It should be that way, that once I find one of the variables, I can plug it back into either one of the original ones to find the opposite variable. So if our x coordinate part of the coordinate is negative 2, the y part of the coordinate is negative 9. So now this is actually the point where supposedly these two lines would intersect if I graph them. So let's see if that's true. Let's see if we use our old method that we know and see if that's really what's happening. So this isn't on your sheet. This is the same example as number 1, but I am just going to prove by graphing, kind of also a review of graphing. So we've got negative 1 as the y-intercept on the first one, so I would start at negative 1, put my dot. If my slope is 4, I remember that's over an understood 1, and so I would go up 4. So up 1, 2, 3, 4 over 1. Keep doing that to be more accurate. So 1, 2, 3, 4 over 1. 1, 2, 3, 4 over 1. I could go backwards if I needed to. 1, 2, 3, 4 back 1. 1, 2, 3, 4 back 1. And do your best to make your line accurate. You guys know I'm never awesome with this little thing. Alright, so now I'm going to try and graph the other one. I would start at a negative 5. Okay, so if I start at a negative 5, and then I would go up 2, so 1, 2, right 1, up 2, right 1, up 2, right 1. Well, see, it's getting further and further away, so I must need to make more points the opposite way. I would go down 2, back 1, down 2, back 1, and the exact point where they intersect, if I graph it very accurately, is at negative 2, negative 9. So we are correct. So we can see that our solution came out to be the same whether we were graphing or we did substitution. So these are just two different methods of finding the same thing. So now let's try this once more. So on number 2, we have y equals 6x and 2x plus 3y equals negative 20. So we already have one of our equations where it's just a variable equals something. So y equals 6x, if that's truly what y is equal to, I'm supposed to be able to take that expression, put it in the opposite equation where that variable is. So we're going to find out by replacing the y. Well, when I do that, 3 was originally being multiplied by y. So 3 is going to be multiplied by the 6x. So the equation I'm really working right now is 2x plus 3 times 6x equals negative 20. And we did that, so now x is the only variable in the equation, and we can try and solve for it. So we've got 2x plus 18x equals negative 20. So when I combine like terms, I've got 20x equals negative 20, and when I divide both sides by 20, I find out that x is equal to negative 1. So now I have the x coordinate to my ordered pair. I know it's going to be negative 1 something, but just like last time, I've got to take that x value and I've got to plug it back into one of the original equations for x. So I can plug it into this really long one, but obviously it's just going to make more sense and be a lot easier to do it with this short one. So if we plug it back in to y equals 6 times x, we're going to do y equals 6 times negative 1. So y equals 6 times negative 1 is negative 6. So now I have my x and my y for the coordinate. So the answer to where these two lines would intersect is the point negative 1, negative. Okay, so at this point I would like you to try the next two on the worksheet. Examples 3 and 4. Try them in the Nearpod and then see how you do. And when you come back, we'll work them together and make sure you got them right. And if you got them wrong, you can see why.